welcome to another edition of the Lab 207 webcast. My name is Vance Kite, and I'll be hanging out with you today as we talk about a changing climate. How do we know what we know? So the focus of this presentation is going to be making a case for the evidence showing us that the climate is changing. In today's presentation, I am going to focus only on things that we see happening right now. And by right now, I mean like as visible and recordable as you look out your window to the thermometer hanging on your deck and you can read the number. I'm not going to engage in any speculation or climate modeling. We're going to deal only in things that we see happening right now. So in building this case that there is a significant amount of visible evidence showing us that the climate is changing, we'll be looking at several lines of evidence. They include the current temperature and historic temperature records, sea ice coverage, glacial retreat, sea level rise, disease patterns, and storm frequency and intensity. So I'm just going to go ahead and jump in and start talking about some of these things. There's going to be lots of graphics, so I'll give explanation to those as needed. You'll see me popping in and off the screen to give you a little bit further explanation. So let's go ahead and just start looking at some stuff. First thing, most obvious is temperature. You have probably seen reports recently that 2016 was the hottest year on record. To go along with that data, 2014 was the hottest year on record, and then 2015 blew away 2014, and 2016 blew away 2015. So there seems to be a trend over the last 3 years that the climate is getting warmer. This is global average temperature. Now, many of you will argue that 1 or 2 or 3 years doesn't necessarily show a trend, but to add to that evidence, 16 of the 17 hottest years on the historical record happened in the year 2000s, or in the 2000s, so since the year 2000. So that shows a pretty decent trend that the average temperature of the world is getting warmer, and then it's doing so pretty quickly. Got some pretty cool graphics that I want to show you on the next slide. Thank you to New York Times for all of these. So first, on the left, you will see a looping graphic, and that graphic basically takes the year and breaks it into 4 quadrants. You got starting with December, and then over on the right, you have got March, and then June, and then I think September is over on the far left. But basically what this graph is showing you is for all 12 months throughout the year, how much did the average temperature of the Earth in that month deviate from the average from 1951 to 1980. So if my words were too jumbled, you can read it at the top of the graphic there. If a particular month's temperature was below that 51 to 80 average, the line is blue. If the month's temperature is above the 51 to 80 average, it is in red. And you will see that as the graphic spirals away with increasing years, getting closer to our present 2017, you see more and more red lines and darker red lines, showing us that we are getting further away from that 51 to 80 average. Now, to break that down a little more granularly, on the top right there, those are monthly temperature records going all the way back to February of 1889 and taking us through March of 2016. Same color scheme. The further above that 51 to 80 average you get above it, the more red or kind of purple pink it is. The further below it you are, the more blue you are. So you can see as you go across the graph from left to right, the monthly average temperature significantly increasing above that 51 to 80 average. The graphic on the bottom shows that 2016 was the first time that the hottest year on record occurred 3 times in a row. So you would usually see like a hottest year and then a cooler year and then a hottest year and a cooler year. 14, 15, 16 was the first time that all 3 hottest years were consecutive to one another. So that's temperature. As the world gets warmer, it makes sense that ice is going to melt. So we're going to look at the Arctic sea ice extent. Basically what happens is every year the ice in the Arctic freezes and it expands out across the ocean, and then during the summer some of it melts off, and then in the winter it's supposed to replace itself back to the level that it was. This graphic right here is showing us, and you can see like that dip. Sea ice in the Arctic is at its highest in the March to April time frame. It is the lowest in the September to October time frame, and then it kind of refreezes. Now, there is significant variation. The gray band across the middle is the range of sea ice observed. The blue line at the top is the maximum sea ice extent for this graphic, and you'll see that's 1979, so furthest back in history. The red line down at the bottom is 2016 and the amount of sea ice that was present throughout the year in 2016. I didn't put 2017 up there because we don't have all the data, but the data that is showing up on 2017 is actually even below the data for 2016. Now, thinking about feedback loops, this is relevant because if there is less sea ice, that means that the reflectivity or albedo of the Earth is lower, which means that it's not reflecting as much infrared radiation out into space, and it's absorbing more temperatures, causing a positive feedback loop where it's going to get warmer and melt more ice. Continuing on with the theme of melting ice, we have got disappearing glaciers. Now, where sea ice is floating out on the ocean, glaciers are hunks of ice that are actually on the land. Talking about two places, Glacier National Park here in America, you can see two photos there. The one from the top is from the 1930s. The one on the bottom is from the middle 2000s. And you can see that it's the exact same location, but where there was once a glacier and an ice cave, there is no longer. Using actual data, in the 1880s, it was estimated that there were 150 major glaciers in Glacier National Park. In 1910, there were still 150 major glaciers, but by 2000s, 2010 I believe it was, there are now only 25 major glaciers left in Glacier National Park. Another study by the USGS showed that Alaska's glaciers are losing 75 billion tons of ice annually. As all that ice melts off land, water is flushed out into the ocean, which is one of the contributors of rising sea levels. So water running off of land causes sea levels to rise. Also, you get thermal expansion where the water gets warmer and it naturally expands. But basically what you see here is sea level data going back to 1980 through the present. The green is tide gauge data, so that would be observed using the tides. And then you get satellite data starting in 1993, I believe it was. But this data shows that globally, the sea levels have risen almost 8 inches since the 1880s. Now, 8 inches doesn't seem like a whole lot, but if your average land area for an island is, say, 2 or 3 feet above sea level, then 8 inches makes a pretty big deal. Or if you're like in the Netherlands or Louisiana and your land actually sits below sea level, 8 inches of sea level rise is actually a pretty big deal. Going to move along from ice and water for a moment and talk about diseases. Now, with regard to disease, certain disease vectors like the mosquito you see here survive in areas that are generally warm and wet. And as the earth warms and becomes wetter, we see the range of mosquitoes spreading out, and along with them we see tropical diseases such as malaria starting to spread. So historically, malaria is usually found around the equator. I will say that there is some debate about whether we can actually see malaria spreading in humans beyond its normal range of the tropics, but there have been studies showing that malaria in birds, avian malaria, is moving outside of its historic ranges. So where avian malaria would have normally been found just around the tropics, around the equator, researchers are starting to see it further north and south of the equator and at higher altitudes than we normally would. The thinking would be that if we can actually observe and measure this happening in birds, it is likely that the same is going to be happening with humans as well. I'm going to wrap up here with some weather-related stuff. So, warm water, warm oceans are one of the drivers of extreme weather, particularly hurricanes. Research has shown that the frequency and intensity of hurricanes in the Atlantic have increased significantly since the 1980s. Now, scientists, they are a wary bunch that are, they're not fans of making huge pronouncements. They'll say that there is a high likelihood that that increase is tied to human activity, but they also like to hedge their bets a little bit. But either way, even if they do not want to directly tie it and say definitively, we know this is because of climate change, we can see that there are more frequent and more intense hurricanes since the 1980s. Also going along with the weather, we are getting more rain. So increasing global temperatures causes more evaporation from surface water, whether it's ocean or lake or river. That water goes back up into the atmosphere and then it's got to come down somewhere else. So we can see that over time, the change in very heavy precipitation events, so this is like major rain or snowfall events, has increased significantly across America. And actually, as you look, as you move east and north across our map, the percent change in the frequency of those events has gone up quite a lot, which would follow with the logic of having more water in the atmosphere from climate change. And we're going to wrap up. Here's my reference list. If you are interested, thanks for taking some time to follow along through this evidence with me. I appreciate you joining me on the Lab 207 webcast, and hopefully we'll see you again.